So in this video, we're going to see another amazing effect of a transmission line, and specifically we're going to study the quarter wave transmission line. So the setup is as shown in this figure. We have some type of a load, ZL, connected to a transmission line that has a characteristic impedance of Z0. Now what we're really asking is, what happens if I move just a quarter wavelength away from this load? In other words, what will be the input impedance that I will see right here? Let me answer this question first, and then I'll show you why this is useful. Answering this question is actually not difficult at all, because we already have the expression that we need. Specifically, this is the expression that we have found for the input impedance along a length L from a load. It is actually equal to Z0, ZL plus JZ0 tangent beta L, and then the denominator is Z0 plus JZL tangent beta L. Now, when the length is equal to lambda by 4, this tangent beta L actually becomes infinity. So in order to make the calculation easier, I have taken one additional step right here, and so I have divided both the numerator and the denominator with tangent beta L. When I do that, and again, if you consider that this number will become infinity and this number will become infinity, it's actually not hard to show that your Z input has the expression that you'll see right here. Z0 square, the characteristic impedance of the line square, divided by ZL. This is actually a very famous expression, and this is something that I strongly recommend that you memorize. It's actually a really interesting, a really simple expression to memorize, but as you will see, it has a significant impact. What is that? Well, let's consider this problem here. It's the problem of matching a load to a transmission line. Specifically, I will assume that I have a real load whose value ZL is equal to just RL. It turns out, and I'll say something about this in the later on, that it doesn't necessarily have to be a real load. But for right now, let's assume it's a real load. And then what we want to do is we want to insert some type of a matching transmission line here. This will actually be my matching network, such that when I look at the input of this matching network right here, my Z input is equal to Z0. So in other words, what I really want is to make Z input to be equal to Z0 no matter what RL is. And the way I'm going to do that is by inserting a matching network whose length is going to be equal to lambda by 4, so a simple transmission line with length lambda by 4. And what I need to find out is exactly what is the required impedance Z. So in other words, what is the required impedance that I have to insert between my load RL and my transmission line Z0 such that the Z input is equal to Z0. Now, the good thing is that this Z input has an expression that we just found out, and this Z input has the expression of Z square, the unknown transmission line impedance, divided by the load, which is equal to RL. So since I want to make it equal the Z square divided by RL to Z0, it really doesn't take much to see that the unknown impedance Z should be equal to the square root of RL times Z0. In other words, the unknown impedance Z is actually the geometric mean of the load that you have, the RL, and the impedance, the characteristic impedance Z0. So it's such a beautiful and intuitive result for you to remember that I strongly recommend that you do so. Now, as you can imagine, this matching network works perfectly well, but only at the frequency where the transmission line has a length of lambda by 4. What happens if we move away from lambda by 4? In other words, what happens if I change my frequency? Well, I'm not going to get a perfect match, and in fact, if you were to plot the reflection coefficient, you will get a result of this nature. So here I have plotted the gamma L, the reflection coefficient that you would see, as a function of frequency. Now, F0 is my design frequency. So in other words, here F0 signifies the frequency where the transmission line has a length of lambda by 4. And so if I'm exactly at my design frequency, then of course I get a perfect match. But as I move away from this design frequency, gamma L will not be 0 anymore, and it will start rising. Now, how quickly it will rise, it really depends on how close the load RL is to the desired impedance Z naught. If RL is really close to Z naught, then it will actually write in a very forgiving way, as it's shown right here. On the other hand, if RL is really very different than Z naught, is maybe 5 times Z naught or even 10 times Z naught, then it will actually rise very, very quickly, and the result of that is that your bandwidth of matching will be very small. What do we mean by bandwidth? Well, typically we don't care to make gamma L exactly 0. What we care to do is to keep it below a maximum tolerable number. So, for example, in many applications, it's okay to keep gamma L below negative 13 dBs, which is about 5% reflection, or below negative 20 dBs, which is maybe 1% reflection. So once you define exactly what is the maximum reflection coefficient you can tolerate, then you can actually find out exactly how much you can deviate from your design frequency. For example, here I can deviate this much for the case of the RL being close to Z naught, or I can only deviate this much from the case of the RL being very far away from Z naught. So even though the lambda by 4 transformer will match the load RL to Z naught, regardless of how far away RL is from Z naught, the reality is that the bandwidth will change dramatically depending on whether RL is only maybe 20% higher or lower than Z naught versus 2 times Z naught versus 10 times Z naught. Now, the other thing I wanted to mention is that this fantastic result that you see here, which is really a quarter wavelength transmission line placed in front of a load to match it to some type of an impedance, is not just a trick that we do in RF frequencies, but rather is something that we utilize in many, many different applications. And sometimes the transmission line doesn't even look like a transmission line. So let me start with this. These are actually some images that we've taken here at Purdue University. And what you will see here is a radome right here, which has been placed on top of the building I'm currently in. This is actually the one hall. And inside this radome is actually an X-band radar. It's an X-band weather radar that we have installed in our lab. What you will find actually, if you were to open this radome, so here is actually the image where we call it, cracking the egg. This is when the installation was happening. You will basically find this X-band antenna. So the idea is that this X-band antenna is supposed to radiate waves, and these waves are supposed to get out, and then you can basically get some information about the weather. You can get all of these beautiful weather maps that you're used in seeing. But what's the issue? The issue is that if you just leave the antenna like that, then it may get damaged because of wind or because of rain or snow or whatever the case might be. So we like to place around it a protective radome. But if you are not careful and you design the radome randomly, you will be able to protect your antenna, but unfortunately you will create some reflections, because as the incident wave is actually hitting the radome, it's going to find some obstacle and a lot of it will be reflected back. And that's certainly not desirable at all, because the antenna typically radiates significant power, and you don't want a lot of power to hit the antenna back for a variety of reasons. Now, the way we avoid that, the way we actually kill this reflection, is by designing the radome carefully such that it functions as a lambda by 4 transformer. So we design the material carefully, and we design the thickness of this radome carefully, such that all radiation is actually getting out to free space like we want it to be, and we don't have to worry about reflections. Another example I wanted to give you here is actually related to optical frequencies. As I mentioned, this is not just done for RF frequencies, but is also done for optical frequencies. And the example I want to give you is anti-reflective coating in glasses. In the old days, we didn't actually know how to do that. So what used to happen is that you would have some incident light coming. Of course, you want all of this light to come to your eye, but unfortunately, there will be some reflection from this light back because of the existence of this glass. if you can treat this glass with some type of an anti-reflection coating, and this is very simple to do because all you have to do is just spray it, then you can essentially kill that reflection, and that means that you can see somebody's eyes clearly without having any annoying reflections. And again, this anti-reflective coating is essentially a lambda by 4 transformer. So these are 2 additional applications I wanted to quickly share with you, just to see that this concept of lambda by 4 transformer is not just for a transmission line the way we're seeing them in this class, but is actually a very general and very powerful concept. The last thing I want to mention here, and I'll leave you with that, is that it's not necessary to just have a single section transformer, but you can actually get multi-section lambda by 4 transformers. So what we mean by that is that if you have some type of a load and that you want to match, you can get some type of a lambda by 4 transformer here, another transformer here with different impedances, maybe Z1 and Z2. And the advantage of doing something like this is that you can actually make the bandwidth significantly better. So for example, the bandwidth of something like that might look something like this. And so it will be much wider than what we basically had before, where we had a single section. So my very last comment is that I told you that this works well when ZL is equal to RL for a real load. If that's not the case, and if you have to do a matching network where ZL is actually complex, well, all you have to do is insert another transmission line right in front of ZL such that you make it equal to a real load. And as you know, you can do that. Remember back your, well, we will actually see this later on in this class, but you can actually do this when we're going to study the Smith chart. You will be able to understand that it's possible to go from a complex load to a real load just by using a transmission line. So more on that later. Thank you.